The title of this research is Exploiting Temporal Parallelism in Particle-Based Incompressive Fluid Simulation on an FPGA. It is a research done in collaboration between KU University, JAXA and RIKEN. First, a quick overview of this paper. I will start by presenting the background, followed by our proposal, then how we did our implementation, the evaluation, to finish with the conclusion. The target of our research is MPS, which stands for Moving Particle Simulation Method. It is an attractive solution in computer fluid dynamic area. You can see an example of the MPS method on the left. The figure represents the flow of a water column, where each picture is a screenshot taken at a different time. In MPS, the targeted fluids are divided into thousands of particles that interact with its neighbor particles. With tens of thousands of particles that can be computed independently, it is required to use parallel computing. However, the algorithm is memory bound and the search for neighbor particle becomes the main bottleneck. JAXA developed its own MPS algorithm called pflow. It is divided into 5 steps. The first step, compute external forces. The second step, compute an external position of the particle. The third step, compute the density and the new pressure. The fourth step, compute a new position and velocity. And then finally, you can move to the next time step. The search for neighbor particles is performed at the steps 1, 3, and 4 and accounts for 56% of the computations. To search for these neighbor particles, buckets that divide the computational domain are used. A particle is then assigned to a bucket and accessed through it. Here, the particle number 12 has an effective radius in red and its neighbor particles are the particles number 3 and 13. The radius of this red circle is equal to the edge of a bucket. As a particle has a diameter proportional to its effective radius, this gives an upper limit to the number of particles inside a bucket. A typical example of an algorithm that uses this search for neighbor particles is the density calculation. It computes a weight based on the distance between two particles. To get this density, 4 loops are used. First, choose a target bucket, then a particle inside this target bucket, then an adjacent bucket, and finally an adjacent particle inside this adjacent bucket. Then the computation can be done. The target platform of our implementation is an Intel Arria10. We chose an FPGA because of its available VRAM that allows to cache with low latency the particles required for the computation, but also for the presence of DSPs that allows for floating point operations in the latest FPGAs, as well as the high external memory bandwidth. Even though MPS is particle-based, our interest is to use stencil computation methods in MPS. So what is a stencil computation? A stencil computation is when every element of an array is updated following a common pattern. An element is updated from its surrounding elements. So here a buffer in blue is used to cache the memory that is reused. So instead of reading all of the buckets from the external memory, using a buffer, only one bucket is read from the external memory. So 8 out of 9 of the buckets can be cached in this example. Another method is the temporal blocking. It is a method used to reduce even more the accesses to the external memory. The result of the computation of each bucket is cached to compute the next time step. This is because after computing the adjacent buckets to the next time step, a bucket can be computed 2 time steps further. More time steps can be computed with the same output bandwidth. This is the benefit of temporal blocking. By combining temporal blocking with the buffer presented previously, results in consecutive buffer that store the results of the computation at different time steps. So here, the buffer in blue t allows to compute for the time steps t plus 1 and store its results in the next buffer, which will compute and store its results in the next buffer, and finally we'll be able to compute for the time step t plus 3. The size of these buffers depends on the size of the computational domain. Our proposal is to adapt the temporal method to use it with the moving particles in MPS. The difference is that a bucket contains multiple particles that can freely move between the buckets. Also, the implementation is in 3 dimensions, even though the figures are presented in 2 dimensions for clarity of presentation. The full domain is divided into smaller domains surrounded by a halo. In the case of MPS, the particle can move between buckets. This means that a particle that is inside a bucket at a time step can be in an adjacent bucket at the next time step. In the case of temporal blocking, 2 more buckets need to be accessed in 1 dimension to compute 3 time steps. However, for MPS, 3 buckets are required. Let's take an example. We want to compute the particle A. The state of the particle B needs to be known at the previous time step. However, the particle B moved between the 2 time steps and came from the right. This movement made the particle B change buckets. As the particle B needed to know the state of the particle C, then from A, 3 more buckets were added. The radius of effluence of the neighbor particles also depends on the movement of the particles compared to the stencil computation. As a result, the buffer used for the temporal blocking span on 1 more plane than the regular stencil computation, increasing the requirement for memory. And these planes are required to be kept on-chip memory. The size of the halo depends on the degree of temporal blocking. The figure here represents the number of buckets required in 1 dimension for each computation for a degree of temporal blocking of 3. When the number of computation for the first time step is n plus 6 buckets are required for the third time step. As the problem is in 3 dimensions and planes are stored on chip memory, it means that to reduce the influence of these added buckets, the number of buckets computed in the x and in the z dimension has to be taken as big as possible. Preliminary studies show that with the VRAM available on chip memory, an x equal nz inferior to 20 can be implemented, which gives 2 times more computation for the same time computation than for the first. Thus, 2 times more computations elements are required to balance the time required to compute all the buckets. The figure represents an overview of the implemented architecture. The implementation is done in a pipeline fashion, with each bucket processor unit computing a different time step in parallel. As the computations are done in parallel, each bucket processor has to compute at the same speed. As explained before, the number of computation is more important due to the halo when increasing the degree of temporal blocking. Thus, 2 particle processors are used for the 2 first computations. The first module reads the data from the external memory, while the last module writes back to the external memory. The data is passed directly between the module without going through an external memory. Or the data is kept on chip. A particle processor contains a buffer, a distance calculation, a density calculation, and an accumulation. The distance calculation is a simple dot product on the difference between the coordinates. As one particle covers around 15% of a bucket, 8 filters are used to get one output every time step. The density calculation is then used after getting the square of the distance. The number of processing particle module instantiated in a bucket buffer is different for each bucket processor, as the number of computed buckets is different. For the first computation, n buckets are computed. For the second time step, n plus 4 buckets are computed. And finally, for the last time step, n plus 6 buckets are computed. This means that the first bucket processor unit should have more particle processors than the second one, and the second one should have more than the third one. For the evaluation, we evaluated 5 different implementations called TB1, TB2, TB2, TB3, and TB3-2. This means temporal blocking of degree 1, 2, and 3, and with 1 or 2 particle processors instantiated. The target platform is an Intel programmable acceleration card with an R10 FPGA. All the computations are performed in a single precision floating point. For the resource consumption, BROMs are consumed mainly by the bucket buffer. The size of the bucket is proportional to the size of the computational domain, so is the number of BROMs used. Using domain decomposition allows to reduce the size of the domain and so the number of BROMs, which makes the implementation possible. The number of DSPs is proportional to the number of processing particle module instantiated. The main resource used are the BROMs and the DSPs. The main implementation is TB3-2, which makes use of the most of the resource available. The processing time is shown in this picture. The first figure represents the processing time to compute 6 time steps, when the second figures represent the processing time to run the algorithm 1 time relatively to TB1, which is our naive implementation. The results give that TB3-2 speeds up 2.8 times compared with TB1, while the computation time from the first input from DDR to the last input gives the processing time 3% longer for TB3-2 compared with TB1. We also run a naive CPU implementation using OpenMP to parallelize the 3 of the most loops, which corresponds to choosing targeted buckets in parallel. We didn't make an implementation that used the most of the cache to reduce the latency, the computations. And the evaluation is conducted on 2 Intel Xeon Silver. The FPGA implementation TB3-2 is 2.1 times faster than the one conducted on CPU. So finally, the conclusion. We present a novel idea to exploit temporal parallelism in MPS. As the number of particles in a bucket can be assumed, we apply the idea of temporal blocking to MPS. Temporal blocking for MPS differs from stencil-based method since the particles move to adjacent buckets. Our proposed architecture is composed of bucket processors, particle processors, and buffer buckets. 5 implementations were evaluated on Intel R10 FPGA. The number of processing particles and bucket processors affect the processing time and resource consumption. The results show that TB3-2 achieved the shortest processing time and 2.1 times speed up compared with TB1. We still investigate ideas to reduce resource consumption in future work. Thank you for your attention.